Okay, so it's 3 or 4 minutes past. So hopefully everyone has had a chance to join. So let's start with the first talk in the new year for the SNEWS Supernova seminar series. And we're very excited to have Isabel Goos with us today. Now, Isabel's originally from Germany. She's now a postdoc in Paris at APC Laboratory. And together with collaborators, she recently published this paper on real-time characterization of both core collapse supernova and neutrino properties based on the detected neutrino signal. So that's really interesting and highly relevant to, of course, what SNEWS is planning to do. So Isabel, please go ahead.
Okay, thanks for introducing me. Indeed, what I will talk about today is about this paper that we worked on here mostly at APC and well, mostly Sonia El-Hedri, who you must know for sure. But also some more people here at APC, and as you pointed out by all the logos appearing here in the bottom, we worked closely together with some experts on supernova simulations from other labs. So it was a very nice collaboration that gave very fruitful and interesting results that I will show you now. So I am not completely sure if everybody here is normally present, but just in case we have some newcomer appearing this new year. So I will talk about core collapse supernovae, which are explosions of giant stars. Typically, this involves masses above 88 solar masses at the end of their thermonuclear evolution, which give rise to neutron stars or black holes. And in this context, there are still several questions open, but most importantly, about the explosion mechanism. So what conditions need to be met to have an explosion, and what phenomena do favor this? In addition, when a supernova happens for some time, a very, very dense environment happens, and this is interesting in order to see if neutrino behavior in these dense environments can be studied. And at the beginning, so when there is a supernova happening, there are two very important phases that I will mention a lot during the talk. First of all, the neutronization phase, where we have a neutrino burst or a neutrino peak in the luminosity. So this happens when the shock that is moving outwards turns at some point from opaque to transparent, releasing a huge amount of neutrinos that are trapped behind the shock that had previously been created via electron capture. We also have material accreting into the protoneutron star. And so this neutronization phase happens the first 10, 20 milliseconds, but the accretion phase extends over more or less half a second. And what we have here is a stagnation of the shock, and neutrinos are still being produced, and it's believed that this neutrino heating revives the shock and leads to the final explosion. So it has been shown, I mixed these two up, okay. It has been shown in previous results that the neutrino rates in the first 10 seconds, 10 milliseconds after the CCSN onset can be seen as standard canals for CCSN distance estimates. So it's a very interesting observable to take into account. And as far as I know, the current window at SNEWS includes something a bit more, up to 50 milliseconds. And of course, well, this is important when we think of detectors that have lower detection rates, but the weak dependence in CCSN model that we had before is lost a bit with this larger window. And in order to reduce this new residual CCSN model dependence, it has been shown in this other paper that adding a window from 100 and 250 milliseconds after the onset of the supernova helps reducing this. I mentioned all these windows because we will also refer to them, and this you will see in a few slides. So what happens after the expression? So actually, in the first more or less 50 milliseconds, the standard way to see things is that here we have adiabatic MSW transitions. Once the neutrinos leave this region, they start traveling towards us, hopefully. And what happens with the neutrinos in this trajectory can be summarized with these two equations over here. I don't know if you can see my mouse.
Yep.
Yes, we can.
Okay. So flavor composition arriving on Earth can be summarized with these two equations. We have the rate of the electron neutrinos, or the muon and tau neutrinos summarized in this flux with the X, that depend on the fluxes that left the supernova. And we can summarize all this with this survival probability of the electron neutrino. And this parameter depends on if we are looking at neutrinos or antineutrinos, and if what is true is the inverse mass ordering or the normal mass ordering. So, as I said, that's the standard way to see things, the standard model, let's say. But it is possible that there is some new physics happening. So in order to see new physics, of course, we would need to have some distortion in the neutrino fluxes. Otherwise, we would never have any hope to see anything. But this distortion should still be allowed by current observations from other experiments, from other knowledge we have about neutrinos. So new physics should be tied to the conditions that are specific to the CCSN measurements, such as the high density in the core or the long travel between the supernova site and the Earth, among others. And there have been some theories proposed that could substantially distort the neutrino fluxes coming from the supernovae without contradicting anything else. And one of these processes is that of neutrino two-body decays, which is a case study that we will use in this work. So I will come back to this again. So this is, of course, a challenge for CCS analysts like SNEWS, what we all want to see being done is disentangling many things. So neutrino properties like the interaction nature, I just discussed at the previous slide, but also the mass ordering. And well, disentangle this from CCSN localization, which includes angular position distance, and the properties of the supernova, like its mass, and so on. So if what we want is to estimate the position in the sky in order to pass on this information to telescopes, it would seem that the most urgent thing to do is localize the supernova. But here we have to be careful, and this is one important topic that I will talk about in this talk, and it's that neglecting new physics phenomena, if they were present, could bias this distance measurement. And now I'm just saying it, but later I will show it for sure. And one important detail to keep in mind is that depending on what the true scenario is, this can affect each neutrino flavor and type differently. So the things I showed here at the very beginning. So what happens to electron neutrinos and muon and tau neutrinos can be different. And this is where the flavor complementarity of different detectors comes into play. So in this work, what we take into consideration are all these detectors here in this slide. We have a large-scale water chunk of detectors, Hapag-Kamiokande, IceCube, and KM3Net, that are mainly sensitive to anti-electron neutrinos. On the other hand, we have DUNE, that is sensitive to electron neutrinos. And finally, we have large-scale detectors that are sensitive to coherent elastic neutrino nucleus scattering, DarkSide and Argo, which are sensitive to all neutrino flavors and types. So what you see here is a list of detectors, next generation detectors. So CCSNe is under construction, as already exists, of course. So this, but all in all, as a group, it's a group of next generation neutrino detectors, and what we want to do is, well, combine them in order to estimate CCSN distance properties and so on. But I will just come to that. Before we go there, we need to know what simulations we use for the supernovae. So the simulations that we use are those from Segalund et al. Those are one-dimensional simulations. We have 149 progenitor masses at our disposal, with 0H main sequence masses ranging between 9 and 120 solar masses. Of course, we have to be careful because not all of them are equally probable. We will have to include a prior probability on these masses that is proportional to the Salpeter initial mass function. And what we will look at are the time windows that I mentioned here. So I showed you in a few slides before that this 0-10 millisecond window includes the neutralization peak, and that in order to have more statistics, we include some intervals after that. And finally, this interval that is part of the later accretion phase. So all this is inspired by this previous work and really worked out for us as well. And then what we also need is what comes next. So once we have the rates for what comes out of the supernova, we need to simulate the expected neutrino rates at our detectors on Earth. And for this, of course, we use SNEWS. So here we have the reduced interaction cross-sections, detection efficiencies, and the effects from energy construction from snow globes. And we have to be careful to add the Bostonian background for the signal for IceCube and CCSNe in order to be consistent. In addition, what we had to do is include the neutrino decay model in SNEWS, so that had to be coded. So what this model assumes is that a heavy neutrino will decay after a characteristic decay length to the lightest neutrino eigenstate, together with an invisible scalar field phi. Now, this is not completely trivial, but it is possible to simplify this parameter a bit and parameterize it with two parameters. One is the normalized supernova distance R bar, which is this d over R0, where d is the proper distance to the distance to the supernova, and R0 is the characteristic decay length for 10 MeV neutrinos, where 10 MeV is the energy, the most important energy considering neutrinos from supernovae. So in the standard model, of course, the characteristic decay length should be infinite, which leads to an R bar value of 0. And the other parameter that we need here is the branching ratio of decays to active neutrinos that will be visible in comparison to sterile neutrinos. So here we give the possibility of having also sterile neutrinos in the model. Of course, in the standard model, we would have a branching ratio equal to 1. So I can show you in a minute what this implies. I'm sorry for this strange shifts. Apparently, when I generated the PDF, everything moved around a bit. Okay, so before we start looking at results, I will give a quick overview of the analysis method that we use. So what we use is the likelihood approach, or in the most general way, what we will always use is this kind of likelihood that you can see here, that will depend on the CCSN distance d, on the CCSN model or mass progenitor mass m, these decay parameters, and the mass ordering that can be inverted or normal. And whenever we assume that the standard model is true, we can go and fix R bar to 0 and zeta equal to 1. And this likelihood will be the sum of the logs of the logarithms of the probabilities for each number of events. So here you see this I that goes over the detectors that will be considered. So sometimes we will just use one detector. So E just is one. And sometimes we will start combining 2 or 3 detectors. And then, of course, we will have more of these summonds. And each of these terms corresponds to one of the 4 intervals that I mentioned a while ago. So just as a small overview of what you will see in the next few slides, I will start showing you what we can do with when attempting to determine the mass ordering. Then I will move on to the estimation of distance to the supernova. And finally, I will talk about what constraints can be made to the decay parameters. But still, before going there, a little warm-up that is really helpful in order to understand what comes. So what you see here are neutrino rates that will be detected at different detectors. So the first column is for Dune, second one for Hyper-K, and last one Argo. On top, you see what would happen if the mass ordering was normal, and at the bottom, if it was inverted. This is for an 11 solar mass progenitor happening at 10 kiloparsec. And as I told you, R0 equal and theta equal to 1 is the corresponds to the standard model scenario, and then the other values are different combinations of new physics that we just check out in these plots. So first of all, if we look at Hyper-K, which is representative of the group of water Cherenkov detectors that we already have today, what we see is that when we compare the blue standard model line with the others, is that the stronger the new physics scenario is, or the most extreme the new physics scenario is, the higher this upwards rescaling of the electron and neutrinos is. And very similar, but in the opposite direction. In the case of inverted mass ordering, we have a downwards rescaling of the rates. So this is, so now the problem in this case, if we were only to look at this, is that neutrino decays, if they were to happen, they could be confused with the change in distance, because these changes you can see here are really compatible with the plain rescaling of the rates. And so this is one first danger, let's say. Then if we look at Dune, we have something that, well, not somewhat similar, and it's the fact that we have, well, here in blue, you see in the NMO, the standard model curve, which when we have when you have new physics happening, what happens is that well, we have the appearance of neutronization peak, and then the inverted mass ordering is the other way around. So what is really different from what we saw in Hyper-K is the fact that this is a change in shape. So this only affects a small region. And one problem of this would be that one mass ordering mimics the other one, because as you can see, the blue curve in the NMO looks somewhat similar to the green curve in the IMO, and vice versa. And but as you will see, these degeneracies we can lift if we start combining the detectors. But here I'm moving forward a bit, so let's stop a bit. Still, let's go back to Argo. What we see here is somewhat of a combination of everything, but interestingly, with an opposite behavior as D4. So we see a decrease in the neutrino rates in all cases, independent of the fact if we are in the normal mass ordering or inverted. So what before was an inverted behavior, here everything goes in the same direction. It mostly is a change in shape. Well, or let's say the strongest thing that we can observe is also a change of shape. And so one thing that, one example that I wanted to show you here is that imagine that in truth, we had this this scenario where R is 1 and Z is 0. If we only had Dune, we would confuse this with an NMO and a standard model. With only Dune, we would have no way to disentangle this. But if you go to Argo, what you can see that the peak for a standard model should be 1.5 times higher than the peak corresponding to this dashed orange scenario. So this would help us see, okay, something is going on here. We are being too fast if we just look at you. So this is quite well, it's just looking at these plots and describing them. But of course, we will in the rest of the talk, I will show you this in a more formal way. But summarizing, what we see is that well, mostly with hyper-K, what could happen if we did not consider the possibility of having new physics, and there were new physics. What we could have in the NMO is an underestimation of the CCSN distance due to larger rates as expected, and in the inverted mass ordering the other way around. And with the example, I hope I already convinced you that using all detector types at the same time, or suitably, it is possible to measure the distance and identify new physics at the same time. Okay, so let's start, as I said before, with the mass ordering. So what we did here is we calculated the 3 sigma distance horizon for rejecting the inverted mass ordering when the normal mass ordering is a true one, and vice versa. For this, we use the statistic over here. And so what this means is that depending on the distance of the supernova, when you calculate the p-value, the rejection p-value, well, depending on the distance, the rejection p-value will vary, which is also equivalent to some number of sigmas. So what we want to see is what distance corresponds to 3 sigma. And this is what I will show you on the next slide. In order to calculate the p-value, what we need is, of course, a probability distribution of this test statistic, which we obtain by sampling observations from this prior probability down here, where we need prior probabilities for everything. So here, it's the prior on the supernova mass, which is something I mentioned a few slides ago. But of course, we will also need some for the decay parameters and for the supernova distance. For these, we use flat priors. For the decay parameters, it really makes sense. In the case of the supernova distance, this is really the most conservative thing we can do. So if at some point somebody wants to do this in more detail, they will only get better results if they put a more detailed prior on the distance. So this is indeed, as you might imagine, computationally expensive. But the nice thing is that we can do it in advance. I mean, we already did this. And so once this is already calculated and done, the calculation of the p-value and the corresponding sigmas is a fast method, which of course, well, I imagine is what is nice for an alert system. Okay, so what you see here are the results. So on the left, it's the, let's say, the best case scenario that we know for some reason that the standard model is true, and do a fit considering only the standard model. So fixing R and zeta to 0 and 1. And on the right, it's kind of the worst scenario where we have some BSM method, BSM scenario, but we don't know which one, so we have to leave R and zeta open. So on the diagonal, what you see are these maximal distances that can be reached with individual detectors. And then the off diagonals, what happens when you start combining 2 detectors. And you can observe in every case that as soon as you start combining detectors, you can reach much further. And one important thing is that even if we really knew nothing and had these extra degrees of freedoms in the calculation, we are still able to reach 21 and 22 kiloparsec with these combinations here, so Dune and HK or HK and Argo, which means that we are able to reach to most of the galaxy in order to reject one mass ordering or the other. So this means that from now on, I can assume that for the rest of the calculation, we can assume the mass ordering is known. Either it has been discovered by then, or things like this can be done. So next, I will show you the impact of neutrino decays on the CCSN distance measurements, which is, I think, particularly interesting for you. So what you see here is the case of an 11 solar mass progenitor. We assume the inverted mass ordering to be true, and we have some beyond the standard model scenario with R equal to 5 and Z equal to 1. And in these curves, in these plots, you see the measured distance as a function of the true distance for Dune, Hyper-K, and the combination of the two. You see the median values and the 90% confidence intervals. Now, if this estimation is done assuming that the standard model is true, where we have this particular beyond the standard model scenario, you obtain these black curves with the gray bands, which are clearly biased when you look at the red dashed line, which corresponds to the true distance. Now, if we leave the possibility open that that beyond the standard model physics is a possibility, leaving R and zeta as free in the likelihood, and do a BSM fit. In that case, you see in Dune and Hyper-K that we managed to get not rid, but to improve a lot the topic of the bias. But with another problem appearing, which is that the uncertainties increase a lot. Now, if we do a BSM fit, but using Dune and Hyper-K at the same time, we have everything we wanted. Then we almost get rid of the bias, keeping small uncertainties, or keeping them under control. So now, if you in the next slide, what I want to show you is the impact of combining different experiments on this kind of measurement. And for this, well, we cannot look at 1,000 plots. So what we will look only at is this uncertainty band here. So we'll focus on a distance of 10 kiloparsec and look at this width. So you can recognize here in pink the lines from the previous slide, together with many more corresponding to other detectors, individual detectors, or combinations of them. So orange, again, also dark orange, means BSM scenario and BSM fit. On the complete opposite side, if we knew the standard model was true and we were doing a standard model fit, we would have the orange, the dashed orange rectangles. And in the middle, we have a standard model scenario where we don't know that it is a standard model scenario, and we do a BSM fit, leaving the possibility of R and zeta to be free, which is this light orange. So of course, light orange should always be a little bit bigger than the dashed orange. So now the important thing that that we see here is that, well, of course, knowing which scenario is true, this, in the case of the standard model, and not having unnecessary degrees of freedom leads to the best results. So for example, you see here in Dune, and Ice Cube and HK, these rather small uncertainties. And what we managed to do in the worst case scenario, where we indeed have beyond the standard model physics, and we have to fit for them as well, we managed to find a combinations of detectors, for example, Dune HK and Dune Ice Cube, with which we practically recover these the uncertainty bands and well, in the accuracy as well, that was possible in the best case scenario. So, well, this is an interesting result by itself. And all these things likely can also be computed quite fast. So this was assuming, let's see, this was assuming IMO. So I'm using inverted mass ordering in all these plots, but well, in the next, this here is for the normal mass ordering case, where we see something very interesting as well. Yes, so indeed, what I was saying before, that what we for sure wanted to achieve in this case is recover the best case scenario, let's say in some way. Well, in the normal mass ordering, it becomes even better. So this for some combinations, at least. I mean, Dune, if you use Dune alone, you have rather large uncertainties, even in the best case scenario, which become better when combining detectors. Okay, so now you saw, well, perhaps no, but I will point it out in the last few slides, Dune and HK, when combining them, it was very interesting many times. So what we have there is, well, Dune is very accurate. Well, the accuracy of Dune, when you combine that with high rates that from HK, there seems to be a very strong combination. And I will show you here in the last topic that that this can be exploited even further in order to constrain neutrino decay parameters. So here we go back to a nice solar mass progenitor at 10 kiloparsec. We are assuming an inverted mass ordering, and this we understand about the scenario. And what we do is a best by fit and calculate iso-likelihood contours. And what you see here are the results for Dune alone, Dune and hyper-K together, and Dune, hyper-K, and Argo. So when you combine all of them, you get the best result, of course. If you, out of these three, the one that is best performing is Dune, this, which is shown here, and the pair, the subpair that performs the best is Dune and hyper-K. So what you see is that well, the star is the true value, R equal to 2.5 and Z equal to 0.5, and the prediction, well, it moves across a bit, but there is still something very important that we can take out of this, and it's the fact that if you look at the plot here on the right, at what happens for R equal to 0, here R equal to 0 is excluded with 3 sigma from being possible. So if this was really the physics, the true physics scenario, what we could do is exclude the standard model with 3 sigma. When we move to the same plots in the narrow mass ordering, this can already be achieved combining Dune and Argo alone. And in general, predictions are more accurate in themselves in this case. But I think it's very nice to see that even if the predictions are a bit difficult to interpret, let's say, there can still strong conclusions to be drawn. It is still possible to draw strong conclusions. So that's it. So to conclude, I would like to focus on these things. We know that locating a supernova using neutrinos is crucial in order to prepare an observational strategy for the electromagnetic counterpart. Now, measuring this distance, the distance that is needed for locating the supernova, this requires assumptions about neutrino properties. For now, the standard model is assumed, but we saw that if some other scenario was true, this could bias the results. And we showed that combining next generation experiments would allow constraining neutrino properties in real time using only the neutrino event counts in this particular intervals. And this would help improve this distance measurement in addition. Now, we propose a new observational strategy, which we tested with this neutrino decay model. Of course, it would be interesting to see what happens if we expand this to a more general model, which includes whatever theory is possible. So this is some kind of outlook, something that can still be done. But all in all, that's it. And if there are some questions, of course, they are welcome.
Thank you very much, Isabel. That was a really interesting talk. And I can see people clapping in the comments. We've got about 15 to 20 minutes left for questions. I can see we'll have a question from Evan in the chat in a minute. In the meantime, Marta and then Alec.
Yep. Thank you, Isabel, for the very nice talk. I was wondering for the Dune experiment, have you considered only the charge current interaction of μe, or have you also taken the neutral current SNEWS on argon?
No, just we consider the most the dominant channels.
Okay, because I don't know how the statistics compare, but I think that the SNEWS Dune can have as more statistics even than argon. So
okay.
can use its own neutral current. Yeah. Okay, that was my question.
Yeah, no, we did not. We can check this out. Thanks.
Yeah, so my question, thinking about it from the alert side, as you mentioned, we're, assume the standard model. So to interpret your figures in the, we would like to identify a progenitor really fast based on the range or something. We would use your boxes that are labeled standard model or standard model best fit, and be able to then say, if the prior of nothing strange is happening, that we estimate the star to be so many kiloparsecs away. The standard model box, is that correct? Yeah.
So actually, what I have, which can help in this question is, so if so this would, it looks like this when we assume the standard model and we do a standard model fit, assuming that we know this.
Okay, yeah, where the big uncertainty is if it's a coin flip between mass orderings, then we have two widely different parameters. Okay, and then so the width, the uncertainty width here is primarily from what?
So here these uncertainties come from what? Well, I could imagine that, so if we think of this, that whenever we cannot break the degeneracy, we introduce these uncertainties. Whenever it's not a helpful enough combination. But in any case, perhaps also one other thing that is interesting in this direction is the size of this uncertainty as depending on R, because we were happy to see for this particular case of R value and one of these plots that when we look at just Dune and just AK, the bars are big, and when you combine them, they get smaller. But we wanted to be sure that this is not just a thing of having a nice value of R. So indeed, whatever the value of R were, if it were different from 0, this would always be the case when you combine DUN and HK, which is nice to see.
Yeah.
Then unluckily, well, this branching ratio is more delicate. So this has a little impact in general. So there is not a big thing to do in this direction. I mean, given some situations, some things can be said, but it's there it's more tricky. But this comes to my mind now with respect to the bars.
Okay, thank you.
Degef, do you want to go next?
Sure. So just a quick question that is naive, but builds a little bit on the last two. How do these sensitivity curves and contours change as you move the progenitor around? I mean, how statistics limited are you with some experiments? I mean, I expect that DUN would have a substantial difference at 200 parsecs and 30 kiloparsecs compared to the galactic center, whereas, you know, Hyper K, obviously statistics affect everybody, but Hyper K is really sensitive throughout the galaxy. So if you were to put the progenitor at the location of Betelgeuse, how would these change, given that DUN would do, you know, really so much better there compared to like the edge of the galaxy?
Well, I don't know. I have not seen these plots. I don't know if we did them at some point for Betelgeuse type distances. Would be nice to see, of course, you're right. It's well, it can easily be done. So perhaps for some next meeting, if there's 5 minutes to remember this,
just make the same plots for two extreme cases.
Yeah.
I'd be curious.
Yeah.
Very nice talk, Isabel. I had a question about the theory. You're doing neutrino decay. Did you allow for energy dependence of the decay?
No. Wait.
Would that introduce some spectral distortions that break, at least at some low level, the degeneracy with distance?
Good question. I don't remember. The last time I checked on this was July or so. Good question. I'm trying to remember. I think no, but I'm not sure.
I imagine the range of neutrinos that you're particularly sensitive to is as you said, around 10 MeV. But is it like plus or minus 5, or do you have some sensitivity so you would notice some spectral change? The fact that the lower energy neutrinos would decay and the higher ones would not much.
I should check this again. Yeah, yes, I should check this again. I don't remember, but it's also easy to check. So lots of homework. Yeah, you're right. I'm sorry, I don't remember.
That was okay.
I guess I can go now.
Yeah.
Sorry, I missed the first 10 minutes, so this question might already be answered. Can you go back to the plot where you had the luminosities for the different detectors? Yeah, or the rates. Yes, this one. Yeah. I'm a bit confused. Why does the rate go up when you have the neutrino decays?
In this, for example, for Hyper K.
Yeah.
Yeah, well, I for this, I remember doing this exercise. We can try to do this. So let's see. If we have, what we have is heavy neutrinos decaying to lighter neutrinos. So these lighter neutrinos have a certain probability of being seen as electron neutrinos, which favors which is high in the NMO and low in the IMO. I think it goes in this direction. So when you have decays, either you have new particles appearing or you have them disappearing. That's the point. In order to see this in detail, you will have to go back to this slide with these equations here in each case and check one after the next why exactly.
So like where Okay, so where do the decays happen?
Along the trajectory.
And do they happen? And the decay is, it just changes into another neutrino, or there's two particles?
It decays to the lightest neutrino with together with a visible scalar field, and this lightest neutrino has a certain probability of being seen in the end as an electron neutrino neon or tau.
So do you expect it to be in the same? Do you expect it still to be traveling towards the Earth, or would it be traveling, in a different line of sight? In which case you wouldn't see it.
Yeah, no, we assume that it is still on the same track.
Is that so? I mean, is that reasonable?
Yeah.
I think if the energy, if it had all the momentum, I guess it would. But if it doesn't have all the momentum, then
Lorentz boosting will just make it so forward peaked, Evan, that it would be more or less in the same direction.
Because the decay is in the, I see, because it's in the rest frame of the neutrino.
Yeah,
but
so
I mean,
even
how
if
much?
it's isotropic in the rest frame, the lament spectrum is so large, it just gets boosted. So that's very forward peaked.
Fine. Okay. Fine. Okay. Thank you.
Thanks.
Okay. One more question from me, which is more on the kind of practical side. If we want to implement something like this in SNEWS to get better distance estimates, for example, can you give us a rough idea of how long these fits will take?
Good. So let's remember. So everything is quite fast. I think exactly. So the everything is very fast. I think order of 10-20 seconds. The only thing that takes some time, as it is here, are these contour plots, of course. But we were very generous with the grids, probably too generous. So this was the longest thing, and it was taking something like 100 seconds. It can be reduced. There is room for improvement, but everything else is seconds. Yeah, 10 seconds, things like that. Of course, once everything is set up, like what I said, having the probability distributions ready to be used, things like that.
So that's 10 seconds or so, including all the different detector combinations and including different parameter values.
Yeah.
Oh, that's really nice. I was a bit worried about that.
Yeah, no, there's we did all having SNEWS in mind mostly. So whenever things started getting slow, it was okay. Now let's think if this can be done better, because it has to be useful. So yeah, that was a main aim, to be able to have it being used in the end.